Okay, thank you very much. So I'm doing a PhD at KU Leuven in Belgium, yes, together with my promoters Martien Nevers and Max Verlinden. So I'm at the end of my PhD, and today I would like to show you some of the results I obtained. So the title of my presentation is The Influence of the Alpha Grain Size on Internal Fatigue Crack Initiation in Drawn Titanium 6-4 wires. Now you might see this title and think it's exactly the same thing, but I will put a focus on a lot of different aspects. I will focus on the facets and also the wires and not forged or extruded parts. Okay, so the overview of my presentation is I will first, shortly introduce the subject. I don't have to go into detail because thanks to the previous speaker, he already introduced it. Followed by the motivation, why I did this work, the results, some discussion and a conclusion. So now I am about to explain fatigue to this group, which is a strange thing to do, but I will do it anyway. So this is the KU Leuven master key. KU Leuven was founded in 1425. Let's assume that it's made of titanium 6-4, which is impossible in 1425, but we will assume it. So we can load it cyclically and wait for a very long time, the stresses are low, until it breaks. And then in certain cases, we will see that the fracture can start internally and we form some sort of fisheye failure. So this is an actual sample, where we see an optically dark region, which is short crack growth region, followed by long fatigue crack growth and the overload fracture here. Okay, so in the case of titanium, there are almost no inclusions. So we all know the fisheye failures from steel. But in the case of titanium, the internal cracks start from inherent microstructural features. And what we see on the fracture surface are facets. So you see in this picture, the facets, what I call facets, are very planar cracks. So actually every facet is an alpha grain that is broken in a transcrystalline way. In literature, you find that these facets are sometimes called quasi-cleavage facets, and then this term immediately tells us that it's, a bit ambiguous, because there is some discussion on how these facets are formed, how the crack formation occurs. So there's a large group of publications that says that there is a slit end formation, but there are also publications that claim that there is a cleavage fracture, so micro-cleavage of the grains. And my talk is exactly to see which mechanism occurs, and we will try to find this out. Okay, so the motivation of my work. First of all, I chose to use drawn wires, because in drawn wires we get a different crystallographic texture compared to what you find in most publications, so it's mostly forged and extruded forms of titanium. While in drawn wires, we do not have, there are almost no alpha grains in which the C-axis is parallel to the wire axis. So the alpha phase is hexagonal, this is the C-axis. And why is this important? Is because along the C-axis, the alpha phase is very stiff elastically, but it's also very difficult to deform elastically by slip. So we have a few slip systems, the basal, prismatic, and pyramidal, and along the C-axis it is difficult to activate these slip systems. So the second part of the motivation is because we know the cracks start from primary alpha grains, we might we might affect the crack initiation if we change the size of these alpha grains. So that is what I try to do. Then we can go straight to the experiments. So I used 4 microstructures. So these are cross sections of the wire, which is 1 millimeter in diameter. All of these wires are stress relieved and also electrochemically polished. From left to right, so we have microstructures A, B, C, and D, and we see that the alpha grain size increases from left to right. B, C, and D are equiaxed, so in the other direction, grains look similar, while microstructure A has some elongation along the wire axis. So I also look at typical texture. So this is a 1, 0, minus 0, 1 pole figure, so this is a prismatic plate pole figure. And we see that most of the grains are actually, the prismatic planes are perpendicular to the wire axis. If you're not comfortable with the pole figure, I can also show you a BSC pattern. So in this case, all of the bluish grains have a prismatic plane perpendicular to the wire axis. And it's the red grains that have a C-axis along the wire axis, and you see there are almost no red grains. We have a small one here, which is probably secondary alpha. So this is an overview of all the fatigue testing. So the first thing I can tell you is that making this graph took a fatigue testing time of 240 days, because we tested 60 Hz only, with an R ratio of 0.1. And that doesn't include the tests that failed, so the broke inside clamps. Those are excluded, and didn't include the preparation time. So one observation that I made is that in general, if we increase the alpha grain size, the fatigue life tends to become lower. So globally over the entire lifetime. It might not be entirely clear, so I take one example. So we have microstructure C and microstructure D. We can compare microstructure D at a stress level of 750 megapascal, more or less. And we see that they all break at a relatively low fatigue life, while microstructure C, with a smaller grain size, they all break at a higher fatigue life. There's also a large spread in data, of course, because we are testing close to the knee of the fatigue curve, so something like this. So we have a large spread here. The second observation is that there are only 4 internally initiated, internally cracked samples, which I can show you if this works. Well, I can first tell you that there are also run-out samples, so samples that tend to stop because this takes 3.5 weeks at 60 Hz. It's not moving forward. I don't know. It's the PowerPoint stuck. So you can already see them here, 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 and here. So we have 3 samples of microstructure C that have internally initiated cracks, and 1 with microstructure D. But the PowerPoint seems to be stuck. Okay, I'll just go through. There are too many animations. So perhaps while we wait, I can already explain a bit. So we have 4 internally initiated samples, which I will call D for the one with microstructure D, and C1, C2, C3 for those with microstructure C. What you saw is that the one with microstructure D has a lower fatigue life, but we have to be careful with the, with the statistics, of course, because it's only one sample. Maybe we can go directly to slide 6 or something. Maybe slide 5.
Somehow it doesn't react at all. Yes, okay, so thank you. Perfect. Yes, I can continue. So like I said, we have these 4 samples which broke internally, D, C1, C2, C3, no, microstructure D1, 3 with microstructure C.
And we will now focus only on these 4 samples, and we'll look at the initiation location. So basically you have 2 types of internal fracture. One is a typical fisheye, so the location of the initiation is very close to the center of the wire and far away from the surface. The other type is subsurface, so the initiation is not at the surface, but just below. That's the case for these 3 samples, C1, C3, and T. So we can now zoom in on the initiation for all these 4 samples, so the white circles. We zoom in and one more step. So we see in all 4 cases that there are these facets at the origin. So in the case of sample D, they are slightly bigger because the alpha grain size is bigger. So we can use these images to calculate, like the previous presentation, calculate or estimate the threshold stress intensity factor range using Murakami's formula. Although we have to be careful because this was developed for steels, so there might be some adjustments in the future. So we measured the facet containing area, which I also did differently. So in this case I use a freeform shape to closely follow the area that contains the facets. And if we then calculate the threshold stress intensity factor range, for these 4 samples we also see, like the previous presentation, that there seems to be no variation in relation to the fatigue life for all 4 samples. So if I would have used an elliptical shape, like the person before me, these values would simply go up, and they would also be between 7 and 8 megapascal Newton meter, which is in accordance with what you find in literature. So the most interesting thing I found in my results is that the facets are not flat, but there are markings at the nanoscale. So for nearly all of the facets, these markings are linear. So you see if you zoom in on these facets, they have some linearity to them. Also the next one here, there's some linearity to them. But there is one strange facet in sample D. So first of all, in all of the other facets, you can see this linear pattern. But in this one here, if you zoom in, there is a fan-shaped pattern. And it's exactly this kind of marking that in literature has been used to say that there is a cleavage fracture of this grain. So now we come to the big question: are these markings caused by a slip band formation, or is there a cleavage? So how will we find out about this? We will inspect them in detail, and more specifically we need to know if the facet planes are according to a certain crystallographic plane, to a slip system plane or a cleavage plane. So there are 2 ways to do this: non-destructively, which I will skip due to time limitations. Basically, we will reconstruct the fracture surface in 3 dimensions and then measure the facet plane angles, the spatial angles. If you want to know about this, you can ask me maybe afterwards. Or the destructive way, so we cut through the fracture surface by focused ion beam milling and then do an EBSD measurement on this cross-section, which I will show you now. So first for, let's say, the regular facets with the linear patterns, in this case, some in sample D. We cut through 2 facets here, you see them here and here, here and here. And then we do an EBSD measurement, and we see that the facet plane is according to a prismatic plane in these cases. And actually I've made many sections like this, and in all of the cases they are according to a prismatic plane. Even more, if we focus, for example, on this facet, and we zoom in a bit, we see that the linear markings are according to a slip direction in the prismatic slip system. So first of all, the plane is the prismatic slip plane, and the direction is also in the system. So this is a very strong indication that there is prismatic slip band formation that is at the root of the facet formation in this case. So then we look at the strange facet, the anomalous facet, and we do the same thing. We cut through, and we do an EBSD measurement here. And we see that in this case, the facet plane has a near basal orientation, so it's almost parallel to the basal plane. And this is interesting because the cleavage plane in alpha titanium is about 15 degrees from the basal plane. It's the 10-17 plane. So this is some indication that, together with the markings, we see that it's a cleavage mechanism. So then we can compare the 2 possible mechanisms. So in both cases, there will be a localized high stress in the alpha grain, which is well, the result of the local texture. So because it's a combination of certain orientations of the grains. And in the case of a slip band formation, there will be a prismatic slip band in 1 or several grains. which afterwards can develop into a crack, also in combination with the tensile stress component. Well, in the case of cleavage, there is a very high stress on a certain grain that is oriented in a bad way, let's say. And because of this, there can be sudden cleavage of this grain, according to the cleavage plane in alpha titanium, which is this plane. And then we get different markings afterwards on the fracture surface. So which mechanism of the two occurs will then depend mostly on the texture, but also possibly on the alpha grain size, because we only saw this one in the sample with the largest alpha grains. But there can also be other parameters such as the secondary alpha or the beta phase. Hydrogen cannot be excluded, and also possibly chemical inhomogeneities. So I come to my conclusions. I will not go through them because there's technical problems already went over time. So the most important conclusion is we are trying to unify what we find in the literature and say that it's not one or the other, but both mechanisms might be possible, and it just depends on the sample, basically. So, thank you for your presentation.